Hello everyone. In this week we will continue the multi-layer neural networks in deep learning studies. So the objectives of this week is to understand the computational graph, which is a key component for optimizing our neural net. And in particular, we will study how this backpropagation works, and then how to train our neural networks based on this backpropagation. The optimization technique to train our neural net is gradient descent. And gradient descent is the iterative method that allows us to find out this local minimum point given our particular function. So starting from some random position, if our function shape looks like this, and then we consider or compute the gradient at this point, which represents the slope of this line, and then we actually move a little bit towards the direction that decreases this function value. And if we go through this process iteratively, and then we will reach this minimum point. And in case we have many parameters or many input variable, in this case we have two input variable of theta 0 and theta 1, and then consider some function that has some particular value given a theta 0 and theta 1. And then we can do the partial derivative, and then given these computed partial derivatives, and then we can update each individual coordinates based on this gradient descent idea. Given these gradient values, we introduce something called a step size or learning rate, and this is determining how much we move given this gradient values. So this is the predefined parameter before starting our optimization process. And now let's suppose our function f will take the vector of three-dimensional input. So previously we considered the input variable is a two-dimensional vector, and now we consider three-dimensional vector that is composed of these three numbers for our input. And then suppose our function is defined by this equation. So for each particular value of x, y, z, and then this function will generate a particular output, and that will correspond to some height on this function. So the only difference is that the input variable is now a three-dimensional vector. And let's start with this random position where x is -2 and y is 5 and z is -4. And then this computational graph to represent our function can be constructed in this manner. So we have x and y, and then they are added first together. And then later on it is multiplied with another input variable z. And then this one will be our final output. And given this particular value, we can compute all these intermediate values in this computational graph. And let's think about this definition for these intermediate nodes. So in this case of q, it is computed by this, and f can be represented by q times z. And in this computation graph, what we want to do is to obtain the partial derivative or gradient with respect to each individual variable for our function. So what we can do here is that we can compute all the partial derivatives with the input variables as well as those intermediate variables. So if we take the derivative on this equation with respect to these two inputs of an x and y, and then we can obtain those values. And then given this f expression composed of q and z, and then if we compute this partial derivative with respect to q and z, and then we will have these results. So here, when taking the derivative with respect to q, and then all the other variables are considered as a constant. And so z here is treated as a constant, and that's why we obtain the z as our gradient value. Okay, so we can obtain the partial derivatives for each of our internal node, but what we want to do here is to obtain the gradient of our function f with respect to our input variable x, y, and z. So in order to perform this process, let's start with this partial derivative of the given function with respect to this given function itself. And then it is, of course, 1. And let's think about the partial derivatives with z. And then in this case, we obtain this 3 because f was represented as q times z, and thus this partial derivative of z will be shown as q, and q here is 3, which is the summation of these two x and y. And what about the partial derivative with respect to q? In this case, we have to look for this value, and it is shown as z. And what is the value of z? It was -4. And now, given these partial derivative at this node, we can further transform it into the partial derivatives with y and x, which is the input node of this intermediate node. So here what we use is this chain rule. So when taking the derivative with respect to y, and then this value can be decomposed into the product of these two parts. And so this was already obtained as -4. And then what about this value? So we have to take the partial derivative of q with respect to y, which is shown here. And this was the value of 1. So this value times 1 will generate just the same value as -4. So what about the partial derivative with respect to x? In this case, we still apply the same chain rule. So when we want to obtain this value, it is represented as the product between these two, and then this value is corresponding to -4. And then what about this value? We already obtained this value here, which is still 1, and thus the overall, the partial derivative with respect to x is -4. As we saw in the previous slide, given a particular node in our computational graph, suppose we obtain the partial derivative or gradient up to this point, and then when computing the gradient with respect to these two variables, and then we simply multiply this value with the partial derivative with this z with respect to x or y. Let's look at another example. In this case, we first obtain this linear combination of this input variable of x0 and x1, and then possibly some bias term, and then it goes through the sigmoid function, which is defined in this form. Let's construct first the corresponding computational graph. So we have w0, x0, and w1 and x1, and w2, and then each pair is first multiplied with each other, and then they are added together here, and then further added together with this value, and up to this point it corresponds to this linear combination, and then we multiply it by -1, and then we take the exponential of this value, okay, and then we add just 1 with this value, and then take the reciprocal. And that way, we obtain this function. So, this complicated function can be viewed as this sequence of our computational graph. And let's look at its derivative. And let's consider the current input values of all x's and w's as these values. And then the node output in our computational graph can be computed by these values. And then at each node, we can also compute its derivative values with respect to its corresponding input. And let's just go through our computational graph from the end so that we can compute the gradient of each computational node. So in this node, it is represented as this function, and then its gradient value is represented by this, and the current input was 1.37, and then we can start with the 1, which was d of an f over d of an f, and this value is further transformed into this value because x was 1.37, and then we plug this value into this expression. And then let's move on to this node, and then this node is represented by 1 plus x. And in this case, if we take the partial derivative with respect to x, and then it will be just 1. And then the gradient value will be just duplicated here. And then moving on to the next step, this computational graph is this function, and its derivative will be the same. And thus, if we plug this value of minus 1, which corresponds to this x value, and then we can obtain e to the power of minus 1, and then it is further multiplied with this value, and then the resulting value will be this value. And moving on to the next one, it is minus 1 times x, where a is minus 1. And then if we take the derivative with respect to x, and then we will obtain a here, and a is minus 1 in this case. And thus, we just simply multiply this value with minus 1. And then we have add gate here, which we add these two. In this case, as we saw earlier, the gradient is 1 because for this node, we can represent it as this form. And thus, if we take the partial derivative with respect to x and y, each of them will be just 1. And thus, this value of 1 will be multiplied by this value, and thus gradient will be moved as this value and this value. And this gradient value will also duplicated as the same value here. And then moving on to this one, it was w0 and x0, which is w0, x0. And as we saw in the previous case, if we take the partial derivative with respect to w0, and then we consider this as our variable, but this as our constant value. And thus, the partial derivative with respect to this guy is this x0, and then vice versa. And thus, this value is further multiplied by this value to generate this 0.4, and the same value is further multiplied with the minus 1 to generate the gradient corresponding to w0. And thus, we finished computing all the partial derivatives with respect to the input variable as well as all these internal variables. Alternatively, we can consider this entire part corresponding to the sigmoid function as a single computational node. And in this case, the function is defined by this, and then what about its partial derivative? It can still be computed by this manipulation, and then the resulting expression of the gradient of this value will have this representation. And thus, what is this value? It is actually the function output of this computational node, and thus its gradient with respect to x is represented by this. And then when plugging this value into here, and then the resulting value will be multiplied by the original gradient of 1 here, and that way we can obtain this gradient as 0.2. And from these examples, we can identify some common patterns in this backpropagation flow. So in the case of an AND gate, which was defined by x plus y, the gradient of, the partial gradient of x and y will all be 1. So in this case, the previous gradient was just duplicated or distributed as the same value. And then what about this multiplication gate, where we see this multiplication here? And as we saw earlier, this gradient is multiplied by this value to generate this, and this gradient is also multiplied by this to generate this. And thus we can view this as kind of exchanging process of the gradient based on their input values. So we can view it as gradient switcher. And additionally, we often think of this max gate. So in the case of max gate, we can represent it as this form, and it can be further described by these two cases. So in case of this, the partial derivative of an with respect to x, and then it will be 1, and the partial derivative with respect to y in this case will be 0. And also, if y is bigger than x, and then the partial derivative with respect to x is 0 and y will be 1. And thus it can be viewed as routing our original gradient into either flow by selecting the max value. And also this gradient is added at these branches. So if one particular node output is branched out into two different computational graph route, and then the gradient value generated from here and here are all added together into this node. So the gradient with respect to this variable is the sum of the gradient from here and here. And overall, when thinking of the training process of our neural network, we first start with some random initialization by setting up the parameter value that we can change as our variable. And then if we do the forward propagation, and then we can obtain these outputs. And then given this particular output, we can compute its objective function value and also the partial derivatives with respect to each of our variable contained in here, here, and such gradient values are represented by these. And of course, we do not have just the two variables. It will have a lot more number of variables, and then we can still compute its partial derivative with respect to each variable. And then based on the gradient descent algorithm, we apply this step size as a fixed number, and we gradually update the current parameter values. And this is the how this gradient descent optimization works by using the backpropagation process in our neural network. And in summary, this lecture covered what is the computational graph, and in this computational graph we understood how this backpropagation works, and then also we understood the overall process of training our neural networks through first forward propagation and then the backpropagation process to optimize our parameters gradually. Thank you very much.